If you remember, we were discussing this model for degradation. Okay, and we said that actually this is the whole model for degradation. We have one here, degradation, which is a convolutive operation, and then we have additive operation, which is noise. So we started with the simple one, which was the additive noise only, and we ignored units for the previous two classes. Okay, and we said that we can use based on the statistics of the noise. I can decide which filter to use. Okay, like being max or median or averaging filter. Then we discussed some variety of averaging filters. Okay, so this is what we did. Now I'm just going back and we'll start with this degradation only, and then combination of both these two together. Okay, so now in order to move towards this degradation, as I mentioned, that this degradation is actually a convolutive operation. Okay, so what it means is that if you have signal or image, it goes into the system so that it is involved with the system impulse response. Okay, impulse response. Okay, and then added to the noise. So if this is a convolutive operation, it means that the system I'm considering is, and convolution is obeyed, and they are SSIM. Okay, linear space invariant in our case, it will be for linear position invariant, or in the one case is for linear time invariant. Okay, so most of the signal concepts are based on when you consider LPI or LSI. Okay, if it's not linear, then sometimes it's difficult to obtain the or restore the image. Okay, or signal. But in this chapter, our aim is the SSIM. What is linearity? Again, we did this before as well, but just to give you another touch, the linearity means that it satisfies the additive and homogeneity properties. Okay, and if satisfies these two properties, it is linear. And definitely, if it is position invariant, which means that it satisfies the position invariant property, it means that if I shift input, output will be shifted by the same amount. Similarly, additive and homogeneity means that if I add the input, output will be added. If I scale the input, output will be scaled by the same amount. Okay, so we already did some examples. There's a system that obeys this equation. Okay, let's say I have the input image, and what it's doing, the output is the second derivative along x is the y. What is this operator called? Laplace. Okay, so in other words, there is a system that is applying the Laplacian on the image. Is this linear or non-linear? Okay, so for linear, I have to check the scaling plus additive, and then I have to check if it is solution invariant or not. Okay, so how to do that? Okay, or maybe I'll just go. I have the solution, by the way. So let's go with the solution. So let's say the input. Can you see that? Huh? Okay. So let's say the scaling first. I move towards the scaling. There are two ways. Either you do scaling and additive separately, or both together from the equation. Okay. So let's do the scaling. So let's say input is scaled, and I call this as f1xy. Okay. So for this, the output will be what? G1xy. Yes or no? What is G1xy? According to this system, it will be second derivative of f1, second along x-axis, and second derivative of f1 along y-axis. What is f1? F1 is afxy. Sometimes I just remove x and y just to make the things arbitrary, compact. Okay, that's it. So if I just put this one, and this a is just constant, I can take it out. So I get a. If I take it out, I get a multiplied by this thing, and this thing is what? Is gxy. So it means that when input is scaled here, if the input is scaled, here, then the output. So if the input is scaled, output is scaled by the same amount. So it means that the scaling is 6.5. Yes or no? Okay. Since the additive have two inputs, the output from the individual inputs will be added to some. Okay. So let's say I have two inputs, this and this, f1, f2, and called the summation as f3. So for f3, the output will be this. Yes or no? G3. Okay. If I put f3 from this equation here, what I'll get? F1 plus f2, F1 plus f2. Okay. And if I just open that, I can get this term and this term, which is G1 and G2. So it means that G1 because of f1, G2 because of f2. So it means that this also satisfies additive property. Yes or no? Okay. The last is the position invariant. If I just shift input, output, shift input, and then find the output which is G1 due to the shifted version, okay, and put the value the same way I did the scaling and additive, I get these two terms, and these two terms is the shifted version of the output. So it means that this is a linear positioning. Okay. And also, this next question is: the system is multiplicative. Is this LPI or no? I think we did it before as well. But if I just want to find the scaling, this is not satisfied because if input is scaled by a, the output is multiplied by a square, means that this is not a linear system. For position invariant, if I do the same steps, I can prove that this is. It's not LPI, okay, or LPI, okay. So it means if the system has passed both the tests, it is LPI or LSI. So we saw this before that I can write the output in terms of convolution. So that's why the system is LSI or LPI, then the convolution is or the vice versa. Okay. So now go back to the equation. We have the impulse response of the system convolved with the image. Okay. In case of LPI system, and then the noise is added. So before that, I ignored this term. I said okay, the image is only degraded by noise. But in frequency domain, I can also write the convolution as the multiplicative. Now I'll just consider this. So one way to recover the signal is by just if I find this thing or this thing, I can do a reverse operation. So what I did it here, I am doing convolution. So if I go back, what I'm doing is inverse of convolution is deconvolution. Okay. So this is what. But again, I should know these things, either this or this. I should know this. Okay. If I know, then I have to do, and then I go and see how I can recover the signal. Okay. Fine. So again, let's assume you don't have the noise. Like previously, I assumed that we don't have the simple system impulse response, but there's the noise. Okay, so now I'm assuming that I don't have the noise. It's just like this image is passing through the system without noise, and there is the convolutive operation. And image estimate process called the image deconvolution because I'm deconvolving it. Okay, we also sometimes call blind deconvolution. Blind deconvolution is the name given when we want to estimate this function from the image itself. Okay, so blind means that we don't know what is h, what is system, but we're trying to extract this information from the image. So this would call the blind. Okay, so now Okay, so what are the methods? One is the using the image observation. I have the image, just the image. Okay, and I'm trying to extract information from that. The other is by experimentation. I have the system itself which takes the image. Okay, so I will do some experiment on that system, try to extract this H. Okay, which is called transfer function. Okay, in the special domain is called impulse response, in frequency is called transfer function. Okay, fine. Then I can also do mathematical modeling. For example, if there is a process of blurring, and I know that how the blurring occurs, so mathematically I can write equation, and from that I can write it. Okay, so we'll just discuss briefly one by one these things. For example, the estimated by image observation. So what I can do is I have the image, nothing else. So what I will take small portion of the image where I'm certain that I know what's in the image. Okay, if I know what's in it, or I can guess it that there is some pattern that I know. Okay, so I pick that pattern. Okay, and estimate the original or guess the original image itself. Okay, so this is the image, degraded image, divide by degraded portion, divide by the portion that I guessed. Okay, let's assume there's a portion in the image that is just a line. So I know that this is a line. Okay, so I can just try to make it good. Okay, and this is my estimation. So that degraded divide by the estimated or guessed image will give me what? The transfer function. Okay, I have the example as well. Okay. So this is why we have LSI. See, LSI has advantage. If we don't have LSI, we cannot do that. See that? Okay. So let's say this is an image, and this has been degraded, which is very obvious that it's like blurred, right? So I can take a small portion here, and I can guess that okay, here is some object, a dark light. I try to manually reconstruct it or guess the image. Okay. Once I reconstruct the image, restore it. Okay. I take this one. This is degraded one. Divide by this. By definition, first page is this is which domain? Okay, so I cannot divide this by this. I have to take a Fourier transform of this and Fourier transform of this, then divide. Okay, so I took this image, this sub image or a small portion, DFT, which I call it DSU of V, like the previous one. Then guessed it, restored it somehow, and then take this one, take the clean version or the cleaned version, and take the DFT. Find it. So once I divide this by this frequency domain, I get this thing, and this is actually equal to the whole kernel because of the property. Okay, this is the first. Yes or no?
Okay, so if we find the transformation parameter for a version, it's the same
for the whole LSI. Okay, so the good thing is that Linearity has additive property. The other thing is, let's say I know how the experiment is being performed, or I can approach the operators or treatment that I use to take the image. What is impulse response? What is impulse? How I can find impulse response? Let's say you have the system. So input is impulse, then output is impulse response. Okay, so this is what I can do. If I know and I have the access to the treatment itself. So what I will do, I will take the impulse in 2D, okay, and try to take the image of that. What will be the image? Impulse response. Okay, so let's say I take the impulse. This is impulse, right? We have one here, and that's the 0. And if I take the image using our blurry camera, let's say, so it will spread it because of that blurry. So this is impulse response. Okay. Yeah, just point. Exactly. You can use it. Yes. But however, ideally it should be 1 because it's impulse or the data function with the amplitude 1. But it may have, because I said treatment may have 1.1 or 1.2 or 0.9 something, so it can have value other than 1. So in that case, I can just divide by 8. If it is 1, then the output is actually the impulse response. But if it is not 1, then we can just divide by that amplitude just to make sure that it's like scaled. Fine. So the step-by-step process is this. You have the input as impulsive image. Okay. So what is impulsive image? This is impulse, right? Impulse with some amplitude, data function with some amplitude. Impulse have amplitude 1. The data function with amplitude A. I take a DFT. DFT of this will be A. Yes, why we have data function, so our difference of frequency will be a constant. Okay, and you can also try to use the equations that we have for the DFT. You can prove it as well. Okay, now here this is the output g of xy. Okay, the in frequency, this will be g v, and then in order to find the transfer function, I divide this by this one. Okay, and I can use this one to find out the image. Okay, or restore the image. What is the difference between restoring the image and enhancing the image? Okay, here what I'm doing, this image, this is black, right? Yeah. Now this is a very good example because here what I'm doing, restoring or enhancement? Restoring. But previously we were calling it as an enhancement, and it was the same blurry image we are enhancing. So how to enhance this? Sharp, right? Because blurry, we have to make it sharp. So how we are making it sharp? We take the image, try to highlight the edges and make it sharp, right? So it was that's why it's called image enhancement. I am enhancing the image, but here I am trying to do the reverse operation of what has been done. So that's why it's called image restoration, right? So there's a difference between enhancement and restoration. See what I'm saying? Okay, so don't confuse yourself in enhancement and restoration. Okay, now the third estimation of the transfer function is using the equation. Okay, so the example is, for example, if you have an air turbulence and you are taking the picture from satellite. Okay, so this air turbulence, if I plot it and try to do curve fitting type of thing, I found out that the transfer function of this is equal to this. Okay, so this again with some experiment, but using some curve fitting type of thing, that which equation satisfy that. And so this is what U and V. I just take U and V, the location of the element in frequency domain. So I square them, I take the power 5/6 and then multiply with K and then give me the air turbulence. How it comes up, this is curve fitting. Okay, so we will not go detail in how it's being applied. So from the satellite, let's say you are taking the air photo and you see this almost has no turbulence. Okay, but here it's a high turbulence or severe turbulence. Here it is in the middle and this is very low. Okay, so these they can be estimated using different values of K. So we have 3 methods. Okay, now let's say I found H. What to do? So either let's say I find H which is the transfer function. And if the condition is that the image don't have any noise, then it's easy. I divide by h, okay, and I will get the estimated value. But not if we have the noise. If you have the noise, this, and I divide by the estimated value. Okay, so we have, if I put g here from above equation, I get this thing, right? So this will be cancelled this in this term. For this term, you get this thing, right? So what is the effect of this here? If the h value is high, reducing, this will reduce. But if h value is low, and normally this is the case because the transfer function have high and low values. So if that is the case, the high values are okay, but the low values will enhance the noise. Okay, and this is the problem because most of the time the image has the noise, and you cannot say that there's no noise. It's exactly just a confusion. Okay, so it's the same image, so it has convolution effect. This is a transfer function plus noise. Okay, so this is the same image here. This image. Okay, so if I do the inverse filtering, I get this. Okay, yes. So let's see this. We have this image which has the turbulence h, but it has some noise. So if I do the inverse filtering, I get this thing because the noise is enhanced. Okay. Okay. Now one way is that I take this term. This is in after the applying inverse filter, and how to denoise it? One way is to apply the low pass filter. We discussed this, right? Let's apply the low pass filter. If I apply low pass filter, and how I apply the low pass filter, if you remember, I decide and radius outside 40 pixels, I make it 0. So I'm just doing a low pass filter. Okay. Similarly, I can have a 70 or 85. So this is 40, this is 70, and you can see that it's improving. But however, 85 is like almost covering everything. Okay, just a small portion, very high frequencies, I just ignore. So the effect is also the same. You see this one? It did not reduce the effect of the noise, but it smoothened this one because the high frequencies I removed it. Okay, and inside I have taken that inside frequencies are not enough to recover this image.
So you align this low pass filter on this noisy?
Oh yes, on the recovered this one.
Okay.
Okay. Okay, fine. So this is one way, but the other way is the famous Wiener filter, and this is so much famous that it's being still used as a benchmark. If you have another filter, another work, you can use this as a benchmark. Yeah. Okay. So Wiener filters work for noise and convoluted model both. Yeah. You don't need to do any other extra operation. It take into account the noise, additive noise as well. Okay. And the concept is that the filter minimize this. What is this? Mean square error, right? So mean square error. So we have error here, and then we have square here, and we have a mean here. So that's why it's called. Whenever the good thing about mean absolute error or mean square error is that you start from error, then square, and then mean. Okay. So you have error, then square, and then mean. Okay. So mean absolute error, mean, then absolute, and then error. Okay. Sorry, error, then mean. Okay.
So you use this mean square error, you should know the original one, right?
Yes.
Because that came to my idea now.
You should know. Actually, this is the magic. He used this equation. Okay. But at the end, I will try to find a filter that minimizes this. So I will not use the original one. It's like unsupervised. This is the good thing. I will show the derivation. Okay. So the purpose is to minimize mean square error. Okay. Why not other errors? Why mean square error? Simple type of error. Why absolute error is more simple. So just error is also simple. Because I want to minimize, right? So in order to minimize, what I have to take any function, I want to find the minimum of that. Take the derivative, right, from your mathematical law. So if it is the function that can be differentiated. So if I just use the mean absolute error, it's like the derivative. It's not optimal. First, the second, if I just take error, simple error, it is not possible because error can be positive, negative, and can be cancel each other and give 0. Okay, so it has to be absolute and square because it is differentiable easily. Okay, mathematically calculable. Okay. Okay, so let's see some big equations, but derivation is very simple. So basically, here what I'm trying to minimize the error between the original one and the estimated one, right? So in other words, what I'm doing is I'm trying to minimize the error between each of the pixels from the original as the estimated one. Yeah, yes or no? Okay. And what is this? This is basically the energy. Yes, energy, right? So energy from the previous signal processing background, and this is what Parseval's theorem is, shows that the energy in time is equal to energy in frequency. Okay, you don't need to derive it. It's there in signal processing. Okay, let me just clean this up if you can. Don't want so many. Okay, fine. So now we are here. Okay, so we said that we want to minimize either in the time domain or in frequency domain. They are same because the energy should be same. Okay, now what is this estimation? Estimation is if I take the corrupted or degraded image and I multiply by a Wiener filter. What is that? We are deriving it. But let's assume that we have that Wiener filter. So estimated was Wiener filter multiplied by this. Now convolution and linear in frequency domain. So I just multiply. Okay, time by time. Okay, so let's put this one here. I get this term. Okay, and what is GUV? It's like UV F plus noise. Okay. Okay, now just to simplify notation, I just remove the term U and V because they are repeating just to make the things easy. So if I do this, I get this equation, simple one. Okay, and all these values are complex numbers. Yes or no? Yes. Why? For Fourier, this is complex number, right? So if I take an absolute value square of the complex number, I can write this one as like this. Yes or no? Let's say you have A plus JB minus B, right? This is what I did. I just write the conjugate. Okay, and here if I open, I have this is one term and this is the second term. Similarly, we have the same terms here. So if I open them, I get same terms multiply and the cross terms. Okay, now the cross terms will become 0. Why? But how you can make it 0? Okay, so we have now the same terms. The same terms, let me explain. The same terms will come here. Okay, if I multiply this with this one, okay, this becomes this. Yes, and if I multiply this with this, sorry, not this one, this becomes where is that? This one, right? So this is okay. But what about the cross term? The cross term will be this type of term. So if this is the cross term, see, F is the Fourier transform of the image, which is random or deterministic. Deterministic, right? W and H are also deterministic, not random. It's fixed. What is random here? N. So the expectation of all the deterministic quantities is the same. Okay. So the only thing left here is this noise, and noise we assume it to be 0 mean or expectation 0. So if that is the case, this will become 0. The cross terms will become 0. Okay. Or even if it's not 0, it needs to be a constant number, so it's okay. Okay, fine. Is this clear? Okay. Now we get this. The cross terms become 0. We just left with this one here. Okay. So now what is expectation? Mean value. Okay. So I can write this thing as this, like summation over U and V. Yes or no? Mean value, and then divide by the MN. But then this constant number, so we can just know it because at the end we have to equate it to 0, so it will. Okay. So expectation becomes this mean value. Yes. Okay. Now, in order to now my aim is to minimize this error to find W such that this error is minimum. What is W? W is the Wiener filter. So I want to find W that minimize that error, and for that I can just use simple mathematical operation to find the minimum of any function. I take that function, divide by the one that I want to find out. Okay, with respect to the function that I want to find it, and equate to 0. Okay, if I do this, I'm only left with this. Okay, you can just take a derivative of this W. Do I need to solve it or not? Okay, so I have this term and I have this term, right? So I have F is just a 4 because I'm finding the derivative with respect to W. Okay, so this is like just a constant term. And for this one, I can write it in like this, right? Yes or no? Okay, plus n square again is a constant term because I'm differentiated with respect to W, and this will be multiplied with W conjugate. Yes or no? So if I just take the derivative this term with respect to W, okay, that even this term is a constant for this term because I'm taking with respect to W, not W conjugate. So if I do this, what I will get? F here, okay, 1 minus, okay, this will become, sorry, not this. Here it goes there. So this will become, if I take the derivative of this term, this will 0, this becomes minus, and this becomes just H, right? Yes or no? And then the same term, because this term will act as a constant for this because this is W conjugate, not W. Okay, so what it will be? 1 minus H W conjugate, or you can write in this fashion as well. Okay, plus N W conjugate. Okay, yes or no? And then this is the derivative of this, and then I have to equate it to be to 0. Okay, I'm rearranging terms, and because I will get W conjugate, but I need W, so I will just take the conjugate of whole term to get this expression. Okay, and then it's just rearranging. Okay, and getting back to U and V. Okay, I get this term. So if you see this term, this is a kind of a very powerful filter that don't have any ground truth. Okay, the only thing I need is H. If I find out H, I will get this term, and this filter works well if you have the impulse response, the whole degradation model, okay, the convolution degradation and additive noise as well. Okay, is this clear? Okay, so just the same thing. I wrote it in this fashion. If you see here, okay, what is FUV whole square? What we call it? What is FUV? It's a Fourier transform of H. And if I take the absolute square, what we call it? Power spectrum. Okay, so this is power spectrum of the image. This is power spectrum of the noise. Okay, I just define it like SF and SN. Try to rearrange. I get this thing. It's nothing. Just try to rearrange. So let's say I give you an image. How to find this? And okay, so this is the filter W, and I multiply with G to get SI. Okay, okay, yeah. Now the thing is that if I give you an image and H, so what you will do? You will find the Fourier transform of the image, DFT of the image. You will find the DFT of the H, which is the impulse response, and you just put it here. And definitely you should know the power spectral density of the noise as well. To put in this equation, we'll get that. Okay. And now let's say you are actually, let's say you are applying the filters. So how to quantitatively find that your filter is improving the results? Okay, in this equation. So let's say any filter like inverse filter or Wiener filter or any other filter, when you're applying, so one of the things that I need to check is the SNR. So it's like a signal power to a noise power, which is SNR. Okay, so how to calculate the signal power? Just square all the terms, summing them, get the signal power, right? And similarly in the frequency domain, using again the Pascal theorem, get this, right? And similarly, signal power, then the noise, how I can find the noise power? By subtracting the original signal with the estimated one and taking this becomes the noise power. And similarly here as well, subtracting them, get this. So either you can do it in time or frequency or special domain frequency domain. Okay. Because I want the power, because of the power. Okay. Okay. I want to know that in my image, how much is the power coming from the noise. Okay, that's the main. That's okay. So sometimes we can also simplify the Wiener filter by assuming the white noise. White noise means that it is constant spectrum. With a constant spectrum, this term will become a constant. And even sometimes, even we assume that this whole ratio is a constant term. What do we mean by this? Like sometimes goes this. These two things we need to estimate. This is the image power and this is the noise power, which we need to estimate, right? So this is like extra term. So sometimes if you don't have the capability to estimate that, I just replace it with a constant term and try method, try to find out which is the best solution for this. So if you remember, we applied the inverse filter for the image and it was with noise. So what we did, we defined a radius, right? So, this is for the inverse. And here we did just apply the Wiener filter, and you can see it's much more, even if you can observe here, it's much more clear, although it's still here, it's blurry, but in Wiener filter, it's much more clear. So Wiener filter will take care of the noise plus the impulse response of the system as well. Okay, it is a whole package for the degradation. And this is another example. Let's say you have blurry plus noise. Okay, so if I apply, this is applying inverse filter. you cannot see anything. If I apply the Wiener filter, and it's somehow better because the noise and the blur is so strong, it is doing some job, but not that much. Okay. So similarly here, I reduce the noise. Again, the inverse filter does not do well, but Wiener filter still improves. Here, again, the noise, I reduce the level. Inverse filter somehow starting giving some result, but Wiener filter is much better. Okay. And this is a numerical example. If I give you, but this I did it for 1D, and I think it will give you some idea of how to perform the 1D. This is what I'm always doing. Make sure every topic I have two things. One I showed you in the picture, image real image, and then I do numerical. So make sure that you understand all these. So let's say here is given a power spectrum or the power spectrum of the signal, 1D signal. I have been given impulse response, okay, and I have been given a power spectral density or power spectrum of noise, okay, and I have been given the output after the correction in time. This is because 1D signal, so it's in time, okay, for the samples. So first I have to take the DFT of the impulse response, okay. I get the C domain version of the impulse response or the transfer function. In the formula, I have this term. Remember that Wiener filter, you have this term, right? So I just calculate multiply term by term by h dk and the complex conjugate of that. Okay, to get this value. Then what I have, okay, I have to build the filter. So I use the formula of the Wiener filter, this one, this one. Okay, I take each term, take this term, divide by this term, and multiply with this, and add whatever, add and multiply whatever, and to get term by term value. So I get this thing as a Wiener filter. Okay, once I get the Wiener filter, I multiply with yk. What is yk? Yk is the frequency transform of or DFT of yn. Okay, we discussed one metric which was SNR. Okay? But in an image, as I explained here before, that not one metric will be enough. Okay, because SNR itself is just giving you how much power noise in the image, but it does not show that the texture is preserved or not preserved, or the things that I am looking in the image is preserved or not preserved. So instead of just using SNR, I also use some other quantities. One is mean square error, which is just the power of the noise. So the more MSE is, more noisy the image will be, and less. But for SNR, it's opposite. More SNR means better derivation, less noise. Okay. Then we also have a PSNR. PSNR is like SNR, but on the denominator, it's like the power, the maximum power, the peak power. The peak power of the image is, I know that in for 8-bit image, it's like, okay, so the only thing I need here is the mean square error. So it's like peak divided by the noise power. Okay, that's it. So these are three terms. There's one more advanced term which takes into account, because all these terms, they just look into how much noise is there, but don't look into the textures, how much texture is preserved, how much details are preserved. This is not there any considering. So most of the time also, if you see any image processing paper, you will find out that they use also SSIM, which is the Structural Similarity Index measure. Okay, so it takes into account all the things together. One is the luminance, which is the brightness, how much brightness is preserved. I'm comparing two images. One is the original, one is the denoise. So is the brightness preserved or not? Okay, what is the brightness? What is the overall brightness of the image? What is the average brightness? Okay, if you have an image, you have values. Yeah. Each intensity between the value and the brightness value, right? Yeah. So if I say what is the average, you take the average of that. So the luminance or the brightness is the average value of whole of that. So what I'm doing is I'm taking the luminance and compare the one image that I have, the other image, the respective image, and try to see the average brightness in both should present. This is one of them. Which is better than SNR. SNR calculating how much power I have. This is what I'm saying. Okay. The other is the contrast. Contrast is like difference between the various intensity levels. So in one image, which is our original image, the difference in the various intensity levels, average difference, and in the reconstructed, the average difference should be same. So it means that the intensity level variations. What is the intensity difference level contrast? It's a variation. So first is related to the mean. The second is related to the variation, which is variance, right? And the third is the structure. The structure means that all the lines should be aligned, right? So in order to compare to the structure, I use the covariance between the two. Okay, so this is what, and I just multiply all of them. Alpha, beta, gamma is just a constant number. And here you see this luminance, I define it like this, which makes sense. Why? Because what is mu x and mu y? Mean value of the original image and mean value of reconstructed. So if both images have the same brightness, what would be the value of luminance? 1. Okay, and if they are not, it will be less than 1. Okay, so it means the luminance value goes from 0 to 1. 1 means perfect, 0 means no. So this gives you an indication. Similarly, the variation. If both variations are same, it means that this is 1, and 1 means that variations are same. If 0 means no variation. And then we have the covariance or cross correlation. Okay, about the two. If I take one image, cross multiply it, take the variance, this becomes this. So it means that if both are same, this both will become same, and this is 1. So it means all these quantities become 1 when everything is same. Otherwise, no. Okay, and I just put everything together here. I will get this simplified form. So yeah, so next topic will be related to the edge detection or segmentation as well.